let's talk about oxidation-reduction equations, how to identify them and how to balance them. First of all, why don't you try to balance this equation by inspection, just moving things to the left and the right, and let me think with you on this. There's 3 reactants and 4 products. It looks like the manganese is being changed and the iron is being changed. There are other anions. Chloride is involved. And how are you going to balance this? How many days is it going to take you? You need 3 chlorines on the FeCl2 to balance on here and a 2 here, but then your irons are unbalanced. That just doesn't look right. So let's first talk about identifying redox equations. They're not ion swaps. Here's a precipitation reaction. You see that really nothing's happening. You just got these lead plus 2 ions that are now attached to iodide on the right when they were just in solution on the left. So this is not an oxidation reduction. The lead was in a sense dancing with the nitrate, ran into the iodide, and then we say they eloped. They formed a permanent solid that left the sodium and the nitrate in solution. And you remember that picture. We also know that it's not an acid-base ion swap. Redox reaction is not like this. Hydrochloric acid reacting with sodium hydroxide forming water. The hydrogen ion is reacting with the hydroxide. That's the net ionic equation for all acid-base reactions. And the sodium and chloride are left in solution. So you start off looking like this, and you end up looking like that. No real change in the oxidation number on the various ions. Okay, well, let's look at assigning oxidation numbers as our first step. Oxidation number assignment is a bookkeeping device. We assign the oxidation state to atoms according to various rules. It may not actually, and usually doesn't, correspond to the atom's real chemical situation. For instance, manganese can have a +7 oxidation number, but you don't have something like manganese heptachloride. A bonded atom's oxidation number is the charge it would have if the electrons in the bond were assigned only to the more electronegative element. In other words, we're treating things that may be covalently bonded as if they were ionic. Here are the rules. First of all, monatomic ions, the oxidation number is the same as the charge. So for instance, sodium plus, oxidation number is +1. Iron 2+, the oxidation number is +2. Chloride, oxidation number is -1. Hydrogen is considered +1 except in the rare occasion when they're with a metal as a hydride. Oxygen is -2 except in the rare cases when we treat them as peroxides, as in hydrogen peroxide here. And elements are always 0. That's very important. So, oxygen gas, O2, or sodium metal, or aluminum metal, or phosphorus nonmetal is 0. Now, for any neutral compound, the sum of all oxidation numbers must be 0. So in carbon dioxide, the sum of oxidation numbers is 0. And of course, that means if the oxygen is -2, that the carbon must be +4. For a polyatomic ion, the sum of oxidation numbers must equal the ionic charge on that ion. So in the ammonium ion, the sum of oxidation numbers is the same as the charge +1. And permanganate, the sum of oxidation numbers is -1. We'll see in a little bit that that's why we can assign a +7 to the manganese in permanganate. All right, let's look at some examples. Ozone. It's an allotropic form of elemental oxygen, so it must be 0. HBr. Well, hydrogen's +1, so the bromide must be -1, as we would expect from its position on the periodic table. Dibromo oxide Oxygen is always -2, so in this case the bromine is +1. We didn't say that oxidation states can't change. They do. When in doubt, check your periodic table. Now a few more difficult ones. CO2 plus, yeah, it's +2. CO4 plus, +4. CrO4 taken twice. What's the chromium? Well, the oxygen atoms are -2. There's 4 of them, so the total is -8. But -2 is peeking through as the charge on the total ion, so all you have to balance off is the -6, so the chromium must be +6, hexavalent chromium. There is the math. And +6 balances -6. So, determine the oxidation numbers of each element, and then check your work by turning on the video again. Now in a redox reaction, at least 2 elements are going to change their oxidation number. So let's look at a reaction you may have studied because you did it in the lab. Silver nitrate in solution reacts with copper metal to form silver metal and copper nitrate solution. And this, of course, looks like silver, and this is a blue solution. The net ionic equation, silver plus reacts with copper, which is a 0 charge, to form silver, which is a 0 charge, and copper 2+. The oxidation numbers are assigned as here, +1, 0, 0, and +2. We then determine the half reactions. We separate the oxidation reaction from the reduction and show the electrons. Well, the silver ion must be gaining 1 electron to form silver metal, and the copper must be losing 2 electrons to form copper 2+. So we have the reduction, the silver being reduced to silver metal, and the copper becoming copper ions and giving off 2 electrons. That's the oxidation. So we balance the half reactions separately. The next thing we have to do is balance the half reactions with each other by finding the lowest multiplier that gives the same number of electrons given away and taken in. In this case, if we multiply the reduction by 2, we're taking in 2 electrons as we're giving away 2 electrons from the copper. And so when we do that, we have balance for charge. We can then add the reduction to the oxidation, and we see 2 moles of silver ions react with 1 mole of copper metal to form 2 moles of silver metal and 1 mole of copper 2+ ions. This is now a balanced half reaction. You can put the anions in if you wish, the nitrates. So here's one for you to balance.